Good evening, everyone. Mechanics of Materials, Chapter 2, Strain, Dilatation, and Bulk Modulus. So if we have a cube of unity in x, y, and z, and it just before stresses, and then apply the stresses in sigma x, like sigma y and sigma z in all directions, it will just either expand or decrease if we want to see the change of volume. So epsilon x, if you remember, it's sigma x over E minus nu sigma y over E minus nu sigma z over E. Likewise, you can jot down the same equation for epsilon y, and like epsilon z is the same, but the normal one is sigma x for epsilon x, sigma y for epsilon y, and so on. We call this equation generalized Hooke's law for the multilateral loading of a homogeneous isotropic material. If you want to know what is homogeneous and isotropic material, I have a video on that for a piece of soil sample, but the same concepts apply for mechanics of materials. So I will upload that for you at the end of this video. And then if we have our original sample before stresses, initial volume is just unity 1 times 1 times 1 in x, z, y. It just gives us a volume of unity, and just final volume after applying these stresses. Either they are positive epsilon x or negative, we just use a plus that one. So new volume is 1 plus epsilon x times 1 plus volume epsilon y times 1 plus epsilon z. If you neglect from the small terms of epsilon x times epsilon y, because that's too small, because epsilon x and y and z are by definition they are small enough. If you multiply them by each other, it's a negligible value. Then you can have a epsilon volume of 1 plus epsilon x plus epsilon y plus epsilon z. This is our new volume. So the initial volume was unity or 1. The new volume is this one. And if you want to have like initial volume after stresses, and if we call delta in volume like a parameter like E, that's a 1 plus epsilon x plus epsilon y plus epsilon z minus 1, and we call that like dilatation of a material. And that's the concept of change in volume per unit volume. We call that dilatation. So if you remember the generalized Hooke's law in terms of epsilon x, epsilon y, and epsilon z, and E, we already see E is epsilon x plus epsilon y plus epsilon z. If we replace all of them in the dilatation equation and expand it, you can say in this equation we have the addition of all these three terms, sigma x over E plus sigma y over E, and two of this yellowish, two of this reddish, and two of this bluish color. That's the general equation. Rearrange this equation and it will just gives us a dilatation, or E is equal 1 minus 2 nu in numerator and a modulus of elasticity in denominator times sigma x plus sigma y plus sigma z. So that's the dilatation of a material which comes with this equation. And in another term we do have is a bulk modulus. So if we just consider when a body is subjected to a uniform hydrostatic pressure of P, then you can replace all these stresses by a negative pressure of negative P, negative P, negative P. That's the effect of a hydrostatic pressure of P. So we can take P like here, and a negative, that's a negative 3P, take it to the beginning of the equation, rearrange the equation, and it just gives us E, or dilatation of material is equal to negative 3 over E times 1 minus 2 nu times the hydrostatic pressure. And a new parameter, we define it like K, which is bulk modulus, and that's E over 3 times 1 minus 2 nu. If you mix these two equations, it just gives us a dilatation has an inverse relation with the bulk modulus. We call E, dilatation of a material, and K is a bulk modulus of a material. And the bulk modulus is a measure of a material's resistance to volumetric change due to application of hydrostatic pressure. That's the definition of K. And if you look at to the nature of the formula, and we do know also the stable material in stable engineering material subject to hydrostatic pressure can only decrease in volume. So if you apply a overwhelming pressure to a normal engineering material, again a stable engineering material, it just shrinkage or decrease in that says in that dilatation of material is negative. And then it just says if epsilon x plus epsilon y plus epsilon z should be a negative, it just because this is a negative, k should be positive to keep that relation. So if e is smaller than 0, it just gives us k, or bulk modulus should be a positive material. The negative times positive gives us a negative in e. So if that's the case, a modulus of elasticity is a positive value, so the denominator should be positive as well to keep k like a bigger number than 0. And 1 minus 2 nu bigger than 0, it just says nu should be smaller than 1 over 2. And we also know nu for a normal engineering material is bigger than 1, so the higher limit and lower limit for nu is 0 to half for a normal engineering material. But however, we do have a very few material like some experimental materials such as polymer foams, which they expand when they are laterally stretched, and that's a very weird one, and that gives us a negative Poisson's value for such a material. If you stretch it, it just expand laterally as well. So there are a possibility that we can have a nu less than 0, but for most of the engineering materials, this is the domain of nu. Let's delve deeper in this equation. Note that the ideal material having nu equal to 0. So if we just go by the lower limit, it just says there is a material which can be stretched in one direction without any lateral contraction. So if you recall the equation, if nu is equal to 0 in this equation, we remember epsilon x is sigma x over e minus nu times sigma y over e minus nu times sigma z over e. If nu is equal to 0, it just says these two terms go 0, and it's just like in a multilateral strain, it just work like a single uh, strain material. And on the other hand, an ideal material of upper limit of nu is equal to a half. It just says k goes to infinity, and if k goes to infinity, if nu is equal to upper limit 2 times, it just gives the denominator 0, and it just give us a k of infinity. If k is infinity, e is equal to 0. It just says that's a perfect incompressible material. Thank you. We'll solve more problems in a string.